Okay, so welcome to the very last unit of the grade 11 mixed course. And it's just going to be one look at one last little type of financial application that we might need, and that's it's called an annuity. So an annuity, what makes it different from the investments we've seen so far is there's no lump sum initial principal value that's invested or borrowed. What annuity is just when you make regular deposits or payments into something and just let it grow over time. So a very common example of one of these would be an education fund. So it might be, if you're lucky enough to have your parents contributing to your post-secondary education, they might have done something where starting when you were born, they started putting a couple $100s every single month into an account in your name. And they're not investing a large amount like $10,000 or $20,000 to start. They're just starting by putting a couple $100s every single month, and it's earning interest. But you just keep adding into it in regular intervals, and it does grow quite substantially over time. But again, it doesn't require a large investment to start, just being able to make regular payments into something. So for this first page here, I'm not going to necessarily want you to write much down. I just want you to sort of follow along with with the concept of it. So again, we're looking at a situation here where someone's going to invest $150 each month into an account that earns 3% annual interest, but it's compounded monthly. So how much will he have saved at the end of the year? So if you're investing it every single month for 1 year, that's going to mean he's putting in $150 12 times. Okay, so and what's going to happen, if you remember how the compounding interest formula works, the $150 that he puts in is going to earn interest every single month. But he only puts in $150 for that first month. The next month he puts in $150, which is going to earn interest, but the previous month's $150 is also going to earn interest. So a good way to look at that is actually probably starting at the last payment and working your way back. So what you wind up having here is you have a whole bunch of months. So let's go from month 1, 2, 3, all the way up to 12. Okay, and the payment that he makes in the last month, I'm going to start with that one. Well, it hasn't had a chance to earn any interest, so that really just contributes $150 to the total value that's going to be in that account. Okay, so that's the the amount he puts in the 12th month. Let's dial it back to the 11th month. Well, in the 11th month he puts in $150, and that specific $150 will have earned the 3% interest once. So it'll be $150 times 1 plus I. So remember, if you picture 3% compounded monthly, so it's 0.03 divided by 12. Okay, that's going to be your I. So that $150 has earned the interest once, okay, and that's going to contribute to the total. And then you go back another month to the 10th month, and all of a sudden that one's going to have earned interest twice, and so on and so forth. So each of these payments is going to earn interest a certain number of times, going back to the one in the first month, which will have earned interest 11 times. And the total amount of the value that's in that account will be all of these amounts added together. So again, picture that there's $150 from the 12th month plus $150 from the 11th month times the interest it earned, $150 from the 10th month times the interest it earned, and so on and so forth. So you can find what we call the future value, the amount that this investment is going to be worth at the end of the year, by adding up all those values together. Okay, I'm not going to make you go through all those calculations. When you do, you wind up with $1,824.96. Okay, so that is in theory how an annuity works, but this method is quite complicated. I mean, I shouldn't say complicated, but it's very cumbersome. You can imagine if this had been a 10-year investment, you'd have had to go through 120 different months, and all of a sudden this becomes a much more long and tedious calculation. So the reason I didn't have you write anything down from this slide is because in practice, well, this conceptually this is what's going on, this isn't generally how you go about calculating values of annuities. What you wind up doing is using a formula that lets you calculate the future value. So here's a formula right here, and FV refers to future value, so the amount that the annuity is going to be worth in the future. It's a rather complicated looking formula, but it's all dealing with things that we've worked with before. So I is still your interest rate per compounding period, N is still a number of compounding periods, and the only change is R, which is your regular payment or deposit that's into an account. Okay, so we can redo this exact same example using all the same information just by plugging into a formula. So the future value is what we're looking for, how much the investment is worth. So if we go back to this, we're investing $150 every single month. Okay, it's 3% compounded monthly, and it's for 1 year. So again, the 3% compounded monthly, you take 0.03 and divide it by 12, which gives you that 0.0025, and N is 1 year, but there's 12 compounding periods in a year, so you wind up with an n being 12. And if you have all that, you can run everything through the formula and calculate the future value much easier. Okay, so you can quickly see it's everything subbed in there. So r is 150, 1 plus I is 1 plus 0.0025, which is 1.0025, n is 12, and I is 0.0025. You can run all this through your calculator, and you'll get the exact same answer we got doing it the long way. Okay, so in practice, I would not expect you to draw out a complicated tree like we did on the first slide. You can just, in theory, use the values in the equation. But it's just a matter of knowing what type of problem you're solving. So what makes an annuity problem different from all the ones we've been doing so far in simple and compound interest is you're going to see some sort of reference to a regular payment or a regular withdrawal. When you see something like that, you know you're dealing with an annuity, so you can completely ignore basically the simple and compound interest formulas and just simply deal with the annuity formula. So just keep that in mind. Okay, so once we have this problem solved, all of a sudden, well, how much interest was earned? Well, how much interest was earned? Well, if you think about it, how much money did Jason put into it? Well, he invested $150 12 times, once a month for 12 months. So he invested 12 times $150, which is $1,800. Okay, at the end of the 1 year, his entire annuity is worth $1,824.96. So his interest earned is going to be $1,824.96 minus the amount of money he put in, which again was the $150 each month for a year, which gives you $24.96. So not lots of interest, but again, we're only looking at something over 1 year. If this was an education fund that would grow over 15, 20 years or so, I'll let you try that on your own. You could see it would grow much, much faster. Okay, but again, in practice, when you're dealing with annuities, we have this nice little formula that will help us solve for the future value. Okay, so hopefully that wasn't too painful. Let's take a look at another example together here. So we want to, this girl Jennifer wants to save $12,000. We want to know how much she must deposit every 6 months into an account with an interest rate of 3.8% compounded semi-annually, and she wants to have the money at the end of 7 years. So this is a typical type of problem you might run into. You want to save money for some sort of, let's say, education down the road, and you know you can make regular deposits based on whatever kind of income you have, and you want to know how much you need to be able to save to invest at regular intervals so you can have a certain amount of money by the end of, in this case, 7 years. So useful type of problem to look at, but again, it's something we can calculate relatively straightforwardly. So first of all, just to give you an idea of a guess, let's say that the account earns no interest. Now, the investment's going to take 7 years, okay, and it's compounded semi-annually. So semi-annually is twice a year. So if you're depositing money twice a year for 7 years, that's 14 different payments or investments. So if you need to save out $12,000 and you're over 14 payments, well, your estimate would be $12,000 divided by 14. Now, in practice, it won't quite be that high because you are going to gain some interest, but at the very least, that gives you a good estimate of where your starting point would be. But to now calculate this, again, you just need to figure out what we have and what we're trying to solve for. So we know at the end of these 7 years, we want to have $12,000. Okay, what's that regular payment going to be? That's what we don't know. So what we need to work out is what our I and N are going to be. Okay, so our I, remember just like in compound interest, 3.8% a year is 0.038. Okay, and it's compounded twice a year, so we divide it by 2, which gives us an I value of 0.019. Okay, and then our N, which is the number of compounding periods, well, it's 7 years times twice a year. So that's going to give us an N value of 14. Okay, so at this point, we have that future value equation. We know exactly what the future value should be. We should, in theory, be able to solve for the value of the payment. Okay, so I'm going to set that up down here. I'm going to let you try this on your own. When you sub all the values you know into the equation, try and isolate for R. Okay, once you've done all the algebra, push play again, and we'll go through it together. Okay, so in the end, you should have gotten an answer of $756.26. Let's run through the algebra together. So I started off by plugging in all the values I knew for the future value, for I, and for N. So I got something that looked like this. And once I got it down to here, it really just became a lot of algebra. So what I did first to isolate for R is I multiplied both sides of the equation by 0.019. Just get rid of the denominator there. So 12,000 times 0.019 was 228. And then I was just left with r times that ugly bracket, which was 1.019 to the exponent of 14 minus 1. And then from here on in, it's just, again, trying to isolate r, so I divided both sides of the equation by that ugly bracket, so 1.019 to the exponent of 14 minus 1. Okay, and I just, again, divided both sides of the equation by that. Okay, I won't write that out, but you can see it's going to go in there, which gives me r by itself, and it's equal to all this. And again, running all this through a calculator, you should get $756.26. So again, what that means, if she invests that amount every single, or twice a year for 7 years, she'll wind up with the $12,000 she needs at the end of 7 years. Okay, so a typical type of problem you might run into in terms of annuities. Okay, so here's another type of example I want you to take a look at, and this one's, if you read through it, you'll see it's a little bit of the opposite of the problem we looked at to start off the lesson. So here, to start off, we were making regular payments into an annuity to try and have money at the end of a certain amount of time. Well, this time we want to invest money now. That's going to earn a certain amount of interest, but we want to be able to make regular withdrawals of $1,000 every 3 months for the next 2 years. So again, instead of trying to put money in, we're trying to withdraw money from an account. We want to know how much money we would need to have in order to be able to make those withdrawals. Okay, so the first thing, so again, for this slide, don't write anything down. We're just going to go through the sort of concept of it. Now, first thing we'll talk about here is if you want to be able to make regular withdrawals every 3 months for the next 2 years, so every 3 months is 4 times a year. For the next 2 years, that's going to be 8 different payments, or in this case, withdrawals from the account. Okay, so to talk through the concepts of this, what might be helpful to look at is, again, looking at that compound interest formula. What's different here is you're looking for a starting amount, so what we call a present value, or in this case a principal. So initial amount needs to be in the account in order to have an amount for withdrawal. So just in case, let's say we're trying to take this equation and solve for the principal. We have to divide both sides of the equation by 1 plus I to the n. So you'd have P equals A all over 1 plus I to the n. Okay? And again, using our exponent laws from last unit, this would be the same thing as a times 1 plus I to the negative n, just to have the denominator out of the way. Okay, so this would be if you're trying to solve for a certain present value that you're looking for. So again, what might be a little bit easier here is, again, you're trying to think back. Again, you're taking out 8 withdrawals over the following 3 years, or sorry, for the following 2 years. Okay, in order for it to be able to make those correct withdrawals, the money that was in there has to have earned enough interest to be able to make up for all those withdrawals. So it's almost like you're going backwards from the first example we looked at. So looking at that look at all these withdrawals of $1,000. Each of these is going to have interest that needs to be added onto it. Okay, and what you wind up having happen is you have negative exponents here. So it goes, if you're looking at 3.6% compounded quarterly, okay, again, calculating that I value 0.036 divided by 4, all of these would need to be calculated. Okay, I'm not going to go through the calculation for every single withdrawal, but if you were to put in these values for each one, what you'd wind up with a whole bunch of different calculations that, again, would be related to every single withdrawal that's going to be made from the account. So you're going to have to add everything together here and wind up with, again, being told that you need $7,685.48 in the account initially. And again, this method of calculation, just like the one we saw in the very first start, it's a bit more complicated than what's necessary, because if you're to look at this over, instead of 2 years, let's say it was over 10 years or 20 years, something like that, the calculation would be far too long, far too tedious. And again, I skipped a lot of the work involved in all these because, again, each one of these simple withdrawals would have to do a calculation along these lines to be able to get everything. So I'm not going to necessarily require you to do that on a regular basis, but just like the other situation we had, we do have a formula that comes out of this. So we do have a formula for what we call the present value, the amount you need in an equation right now, in an account right now to be able to make regular withdrawals over a certain amount of time. So that's the formula right there. We're going to talk a bit more about it in part 2 of the lesson, and we'll finish everything up there.